Hello students, welcome to our channel. In this session, we are going to learn about union and find algorithms. In our previous class, we learned about disjoint set operations and we learned about how to represent sets and we discussed about what is union operation and what is find operation. Now, we are going to discuss about algorithms for union and find operations. Union and find algorithms. In presenting union and find algorithms, we ignore the set names and identify sets just by the roots of trees representing them. What it means here, S1 equals to, I am considering 1, 7, 8, 9. Now I represent this S1 as tree. So already we discussed in our previous class. Now, so 1 represent root, the remaining 7, 8, 9. Remaining elements are attached to root. Okay. So now what is the first point? In presenting union and find algorithms, we ignore the set names. Here what is the set name? S1. We ignore the set names here and identify the sets. How we identify the sets? S1 here by using root here. So 1 itself represents the set S1. To represent the sets, we use an array of 1 to n elements. Here we are going to use an array. Now, so this array starting number is 1. The ending is n. There are 4 numbers, then 1, 7, 8, 9. So where n is the maximum value. Here the maximum value is 9. So the maximum value is 9 here among the elements of all sets. Okay. The index values represents the nodes. Indexes represents the nodes and the entries represents the parent. What it means? For example, so this is the S1. I represent as array. This array 2 parts. One is index, another one is parent. Now here the indexes values represent the nodes. What is the nodes here? 1, 7, 8, 9. 1, 7, 8, 9. And the entries represents the parent node. So what is the parent to 9? That is 1. What is parent to 8? That is 1. What is the parent to 7? 1. What is the parent to 1? There is no parent. So we represent as -1. The root value, the entry will be -1. Here this is the root. So union operation. So for the following sets, the array representation is shown below. So this is the S1. S1 equals to 1, 7, 8, 9. S2 equals to 2, 5, 10. S3 equals to 3, 4, 6. So this is the tree representation. S1, S2, S3. Now we represent the trees in the form of array. So here, so this is the index. This is the index. This is the parent. Now represent all the elements as index. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now consider the 10. 10 is the element. What is the parent here? Parent is 2. So I write 2 here. Similarly 9. So this is the 9. 9 parent is 1. 8. 8 parent is 1. 7. 7 parent is 1. 6. 6 parent is 3 here. 5 parent 2. 4 parent 3. The parent means root. So -3. So this is the root. Root parent is -1. So I write -1 here. For 2 it is -1. 1 it is -1. This is how we represent sets in the form of array. So algorithm for union operation. So first we discuss simple union. To perform union, the simple union function takes the input as set roots I and j and make the parent of I as j. Make the second root as the parents of first root. So what it means? So for example, so this is the S1. This is S2. S1 and S2. Here S1 is I. S2 is j. Now we represent, so parent of I, that means parent of, what is I here? S1 equals to j, S2. Now I make second, this is the S2, 5, 10. Now 2 is the parent of S1. Now this is the S1, 1, 7, 8 and 9. So this is the simple union. So now algorithm for find operation, the simple find. What is the find operation? You are giving one element I. Now this algorithm returns the set name. This element belongs to one set. That set will be written as output. The simple find I algorithm takes the element I and finds the root node of I. Here if I give the element as 9, for 9 the root is 1. 1 represents the S1 here. Now if starts at I until it reaches a node with parent value minus 1. So for example find 7. So find 7. How? Here the 1, 7, index 7 entry is 1. That means it have one parent. Now we move to 1. Now how we identify? End of the root parent address is minus 1. So we traverse until the root is minus 1. So this is the simple find. Simple find of 7. Now what is the 7 here? What is I value? I equals to 7. While parent of I, what is the parent of I here? 1, 1 greater than 0. So 1 greater than 0 is true. So I make I equals to parent of I. What is the parent of I here? 1. Again we check that. So what is the one parent? That is minus 1. Minus 1 greater than or equals to 0? False. So it returns I value. Now what is I value? 1. So 1 represents S1. That means the 7 we found in S1. So these two are the simple union and simple find. Now we analyze simple union and simple find. So these two algorithms. So although the simple union and simple find algorithms are easy to state, their performance characteristics are not very good here. So why? The time complexity is high. Let us discuss with one example. So consider the sets 1, 2, 3, 4, n. So these are the sets S1, S2, S3, S4 until Sn. Then if you want to perform following sequence of operations, union of 1 comma 2, union of 2 comma 3, union of n minus 1 to n, the sequence of find 1, find 2 and find n. The sequence of union operation results the degenerate tree as well. This is the degenerate tree. So degenerate tree is nothing but we start from 1, set 2, set 3, set 4 until n. So this we call as degenerate tree. Here if you observe that the time taken for union is constant. So this is the union. What is the time complexity here? P of I equals to j. So it is constant. But if there is n minus 1 sequence of unions here, why? Union of 1 comma 2, union of 2 comma 3, union of 3 comma 4 until union of n minus 1 to n. So the time complexity is big O of n here. For the sequence of find operation, it will take time n, complexity is big O of n square. How? So this is the simple find algorithm. Here we process this while loop up to n elements. So the time complexity is big O of n. Here we are going to find 1 to up to n. So the time complexity is big O of n square. Now we can improve the performance of union and find by avoiding the creation of degenerate tree by applying the weighting rule for union. So weighting rule for union and collapsing rule for find. So now we see what is weighting rule for union. So now, so what we observe? So already we learn the simple union and simple find, but for this algorithm the time complexity is high. Now how we are going to minimize that? So by using the weighting rule for union and collapsing rule for find. So first we see weighting rule for union. If the number of nodes in the tree with root I is less than the number in the tree with root j, then make j is the parent of I, otherwise make I the parent of J. So consider set 1, 2, 3 up to n. These are the sets S1, S2, S3 up to Sn. So union of 1 comma 2. I make 1 and 2. Initially the number of nodes are 1 in all the sets. Next one, union 1 comma 2. You compare 1 and 2, both have the same number of nodes. So I make 1 as parent of 2. Next I consider union 1 comma 3 here. So 1 comma 2 has 2 nodes, 3 has only 1 node. So I make 1 as a parent to 3. So this is the resultant tree. So similarly up to n, this is the up to n. Okay, to implement weighting rule, we need to know how many nodes are there in every tree. So for this tree, the number of nodes are 3. To do this, we maintain count field in the root of every tree. Now for this tree, you are maintaining one count value. Now what is the count of this tree? The count is 3 here. If I is the root, then count of I equals to number of nodes in tree with root I. Here the count of I equals to here 1. So count of I means the number of nodes, that is 3. Since all nodes other than roots have positive numbers, in parent field we can maintain the count in P field of the root as negative number. We are going to maintain the count in the form of negative value. For example, the count equals to 3, the number of nodes. I maintain this as negative value minus 3. So this is the algorithm for weighting rule for union. Okay, so these are the two sets S1 and S2 here. Now we are going to call weighted union I comma j. What is I here? I equals to S1. So what is S1? 1 here. So we represent the S with the help of 1. Similarly, S2 with 2 here. What is I value? 1. What is the j value? 2. Now, so temp equals to P of I plus P of j. What is P of I here? The count. What is the P of I? It contains 4 nodes. So it is minus 4. So P of j, that is 2, contains 3. So we represent as minus 3. So P of I minus 4 plus minus 3. So temp equals to minus 7. Now you compare. So P of I. What is P of I here? Minus 4 greater than minus 3. So minus 4 is greater than minus 3. It is false. So we go to else part here. Now P of j, so parent of 2 equals to I means 1. Now parent of 2 equals to 1. So this is the 1. 1, 7, 8, 9. So this is the 1. Now I make this 1 as parent to 2. So this is the resultant tree. Now what is the count? P of I. So P of I equals to temp. What is the temp here? Minus 7. So the P of I equals to temp. So temp means, so P of I represents count value. Initially it is minus 4. Now we make the S2 as subtree to S1. It contains 3 nodes. So the P of I contains minus 7. So now we see, so collapsing rule for find. So consider the tree created by weighted union on the sequence of I greater than or equals to 1 and less than or equals to 8. So these are the union operations. Union 1 comma 2, union 3 comma 4, union 5 comma 6 and union 7 comma 8. These are the sets. Now what is the root here? Minus 1 root, minus 1, 3 root, minus 1, 4 root, minus 1, 5 root, minus 1, 6 root, minus 1, 7 root, minus 1, 8 root, minus 1. So that means these are the roots of the sets. Now union of 1, 2. So this is the result. 1, 2. Union of 3 comma 4. So this is the resultant tree. And union 5 comma 6. This is the resultant tree. And union 7 comma 8. Now union of 1 comma 3. So union of 1 comma 3. Now this is the union of 1 comma 3. So union of 1 is 1, 2. So this is the 1. 3 means 3 and 4. Now what is the union here? Union means you are going to find the number of nodes. For this minus 2. So for this minus 2. Now 1, 2 and you can append this 3 and 4. That's it. Now this is the 1, S1. Similarly, union of 5 comma 7. So this is the 5 and this is the 7. So the resultant tree is 5, 6, 7, 8. Now you combine union 1 comma 5. What is 1 here? This is the 1. 1, 2, 3, 4, 5, 6, 7, 8. Now you are going to perform union operation. So this is the resultant tree. So what is the resultant tree here? The resultant tree is, so 1 is root, 2, 3 and 4. So this is the S1, that is represented as 1, and another one is 5. So 5, 6, 7 and 8. Okay, so this is the final version of union 1 comma 5. So this is the algorithm for collapsing find. You are going to find root of I value. We discuss with one example. First we see the algorithm. While parent of R greater than 0, do R equals to parent of R. That means you are trying to find the root of the node. So while I not equals to R, we are going to find S equals to parent of I and parent of I equals to R and I equals to S. Let us consider this tree. So what is the tree here? 1, 2, 3, 4, 5, 6, 7 and 8. So this is the tree they given. Now we are going to find one value in this tree. For example, I want to find of 8. Okay, find of 8. Now 8 is I value. So what is I value here? I equals to 8 here. So what is the first instruction? Same algorithm I write here. The same algorithm I represent here. R equals to 8 here. While P of R, that means the parent of R greater than 0. What is the parent of 8 here? So parent of 8 is 7. 7 greater than 0. True or false? 7 greater than 0. So we do R equals to parent of R. So 8 parent is 7. Now R equals to 7. Again you are going to check that P of R greater than 0. So what is the parent of 7 here? Parent of 7 is 5. 5 again greater than 0. It is true. So make R equals to parent of R. Parent of 7 is 5. Next, now parent of 5. So what is the parent of 5? 1. 1 greater than 0. Yes, it is true. So R equals to 1 now. Now again move to parent of 1. So what is the parent of 1? Parent of 1 is minus 1. Here minus 1 greater than 0. False. Now what is R value? R equals to 1 here. Okay, you remember this. R equals to 1. Now while I not equals to R, what is I value? I value is 8 here. 8 not equals to 1. R value is 1. Now we are doing S equals to. So parent of I. What is the parent of I? 7. So parent of 8 equals to R. What is R? R is 1 here. Now, so this 8 parent is 1 now. So this is the 8. So this we call as collapse. Next one. Again we go to R here, we update the I value also. I equals to 7 now. Next iteration. What is I? 7 not equals to, what is R? R is 1. S equals to parent of 7. What is the parent of 7? 5 here. Now parent of I value is 7 equals to R. Now the parent of 7 is 1 and update the I value. I equals to S here. What is S? 5. Again you check that 5 not equals to 1. Yes, it is true. Enter into the block. S equals to parent of 5. What is the parent of 5? 1 here. 1 and parent of 5 equals to R. R is 1. So parent of 5 is 1 now. Next I equals to yes. What is yes? 1. Next iteration 1 not equals to 1. It is false. Now so this is the resultant tree. So what is the advantage of collapsing rule for find? If it is simple union, to retrieve the 8 we are going to do 3 comparisons. 3 comparisons. For example, I want to search 8 30 times, then I am going to compare 30 into 3 90 times. But here in collapsing rule find, when we find the root of 8 is 1, we make 1 as root to the 8. So next time onwards, first time in collapsing rule also we are going to find, so we are going to compare 3 times, but next time onwards we are going to reduce the comparison times. So directly you find that 8 belongs to S1, similarly 7 belongs to S1. Now the time complexity will reduce in collapsing rule for find algorithm when comparing to simple find algorithm. So this is the end of unit 1. Next class onwards we are going to start unit 2. In unit 2 we are going to discuss about 2 techniques. One is divide and conquer technique, another one is greedy method technique. In next class we are going to discuss about divide and conquer general method. Okay, thank you.